Good morning, everyone. Today we are going to continue our talk about phase diagrams because it is very important to understand the phase diagrams for all these mechanical engineering students. In today's lecture, I'm going to repeat several important concepts for all you guys to refresh your memory and also reinforce understanding of these important concepts. On the first one, we talk about components and systems. Last time we talked about these two concepts, but now I want to refresh your guys' memory. The components here, it means pure metals and all compounds of which no alloy of which alloy is composed. These are, for example, the components are copper and zinc in a copper zinc brass. And we have the concept of solute and solvent based on our daily experience, and we know the solute and the solvent, right? When we mix the sugar with the water, and the solid sugar is solute, and the water is solvent, and finally we get the solution. This is a component. Then we talk about systems. In this context, systems refer to refers to a specific body of material and consideration, for example, a lead of molten steel, or it may relate to the series of possible alloys consisting of the same components but without regard to alloy composition. For example, iron carbon systems. And I also told you last time that iron carbon system is the most important um, the phase system, the phase diagram, and we are going to learn in this class. And physics, and the physics means that uh, the physics is a material, right? So this is when we talk about solubility limit and the solution, a solid, liquid, or gas solutions, single phase, a mixture more than one phase. Here is the solubility limit. Solubility limit. Here we still use the example of sugar slash water, um, the phase diagram. So here is the water, and water is 0. This is water. Okay, C here is the composition of sugar. At the very beginning, is 100% of this material is water. And we can add this sugar in the water, and we can get this is the sugar water. You can see the different temperatures, and we can this water can dissolve different weight or percentage of sugar in the water to get the sugar solution. So solubility limit here refers to maximum concentration for which only a single phase solution exists. So question, what is the solubility limit for sugar in water at 20 degree C? So for this problem, you can just 20 degree and draw a horizontal line. And this horizontal line intersects this blue curve. And at this point, then through this point, you draw a vertical line. This vertical line intersects this x-axis at some point here. It's about 63 or 64 something. Let's see what we can get. So here, we can get this 65. Right? So at 20 degrees C, and if this concentration of weight of sugar is less than 65, and then that means we will have um, uh, the syrup. The syrup is a liquid solution. And however, if at this temperature, if the uh, composition of this sugar is more than 65, and that means, and we will have liquid, both liquid and also solid sugar here, and that means this is the point here, and we will have two phases. One is liquid and one is solid sugar. These are two phases. Uh, if we change the temperature, then we can change the number of phases. And so this one has been shown. And you can see change the temperature here. Okay. And so, for example, pass to from A to B, from A to B, the same the concentration or the composition of sugar, and from A to B, the temperature changes from 20 to 100 degree. And you can see at this point A, we have two phases, L plus this S. However, and if we increase the temperature at some point, here is around 60 degree C. So this is all this is a solid sugar, and will be dissolving in the water, and then we will have a single liquid solution. And so this is the L here. Below this 100, at 100 we can have the third. This is the phase. The third phase is a vapor, right? The evaporation will occur. Then altering C composition can change the number of phases also. For example, and at this temperature, which is a little bit lower than 100 degrees C, the evaporation temperature, and here you can see, and this from B to D. Alright, so B is 100. If you just increase the composition, and after this is pass, and intersects this blue curve, and we will have two phases. One is still L, which is liquid. Another one is the solid S. We have two phases. That means, and to the right of this blue curve, we have two phases, and to the left of the blue curve, we have single phase, which is liquid. Any questions so for this slide? No question? And then we talk about several important concepts here. Phase equilibrium. And first one is the free energy. Okay, and last time I talked about this one, but as I said, phase diagram is the most important topic in this material science class, so it does not hurt and to for me to repeat this one. Phase equilibrium. And first one is the free energy. And it is a function of internal energy of a system and also the randomness or disorder of the atoms or molecules. And second concept is equilibrium. A system is at equilibrium if its free energy is at a minimum and some specified combination of temperature, pressure, and composition. I want you guys to draw and score these three factors that affect the phase: temperature, pressure, and composition. So these are three commonly used factors that affect the phase diagram. And then talk about phase equilibrium. And phase equilibrium refers to equilibrium as it applies to systems in which more than one phase may exist. I'm sorry. And it is reflected by constancy with time in the phase characteristics of a system. And the fourth, the concept is metastable state. And it is often the case that a state of equilibrium is never completely achieved because the rate of approach um, to equilibrium is extremely slow, and such a system is said to be in a non-equilibrium or metastable state. A metastable state or microstructure may persist indefinitely, and experiencing only extremely slight and almost imperceptible changes as time progresses. And I want you guys to understand these concepts and make sure you can use your own language and to describe and to explain these four concepts. Um, if you can use your own language to explain any, not just these concepts, any concept, and that means that you truly understand this concept. And however, if for some reason you could not explain the concept using your own language, it means that to some extent and you still do not understand completely the concept. So this is how we did approach to learning things better. Make sure and you can understand, explain this concept or any series or anything to another people using your own language. If you can make it, and that means you can 100% sure, 100% understand this concept. Otherwise, to some extent, um, you are not very, very clear, right? So this is a very, very good learning strategy using your own language to explain anything you just learned and to your peer students or to your friends or maybe to your brothers and sisters. Maybe you can just explain this to me in my office if you want. Um, for then we talk about the one component unitary phase diagram. And so this is the pressure and temperature, and one component. Okay, so this is the most commonly see example is the water. And water has three phases: liquid water, solid ice, and the gas is a vapor. Okay, so this is the three, the steam. Um, so here, you have this one, this is the temperature, and here is the phase, and here is the this is pressure. I'm sorry, this is pressure. Uh, for this pressure, you can see pressure and the temperature and can affect the phase. So for here, for this area is solid S, in this area is water, in this area is the steam. And the phase diagram, uh, we talk about unitary, and then we talk about uh, the phase diagrams indicate the phases as a function of temperature, composition, and also pressure. And for this course, okay, for binary systems, and just the two components, and independent variables, we focus on the temperature and composition. And the pressure, we use one atomic atom atomic state. Use we use one as ATM, and so this is the air pressure. Okay, so this is the um, uh, P equals one. This ATM, and this because all these temperatures, and here the plane in the this is the um, just around this Earth's surface, the temperature, the pressure is 1 atm, and because all these is activities, and let me see, not all, most of these activities um, happen at this temperature, this pressure. So as a result, all these materials and phase diagrams, we just assume the operating pressure equals 1 atm. So as a result, we only focus on the temperature and the composition in our this phase diagram. So for here, this is a two phase diagram and the copper nickel system. And so here is the temperature, degree C, and here is composition. This is the weight percentage of nickel. And you can see clearly that so this is solid solution can exist from 0% of nickel to 100% of nickel. And so within this phase diagram, and there are two curves. One curve is solidus. Below the solidus, all this is the phase is a single phase FCC solid solution. Above this liquidus curve, it is a liquid. In between, between this liquidus and solidus, we have two phases. One is uh, the liquid, another one is the solid alpha. Uh, we have three different phase fields. Okay, L solely the liquid, alpha solely solid, in between, and L combination of L plus alpha. Any questions regarding this slide? And then we talk about isomorphous binary phase diagram. And isomorphous, as the name suggests, iso means something is the same. Here, we can see isomorphous. For this is the uh, excellent example, copper nickel system. Isomorphous means that complete solubility of the compound component in another. This alpha phase field extends from 0 to 100% of this nickel. For this is a very, very good, excellent example. Uh, so this is isomorphous. I hope you guys um, can remember this one. ISO, whenever you see ISO, it means something is important. Morphous means the morphology, morphous the shape, and you can just see the shape morphous something is the same. And criteria for solid solution, okay, so for isomorphous, for example, nickel copper solution. And so these guys, we have three um, the criterion. So first one is the straight crystal structure, and these two guys must be similar. FCC, or BCC, or HCP. And if this one does not match, if these two guys do not match, and it's very, very hard for you guys to get um, the solid solution. The second one is electronegativity, which is very, very close. Electronegativity determines the chemical, um, this is a chemical um, reaction, chemical uh, reactivity. So be very, very careful about this electronegativity. And then the third one is the radii of these two guys must be close. Otherwise, you cannot form the substitutional solutions. You can see both of these, they called W. Hume-Rossery rules. So these are the rules. These are two scientists, and they found these rules, uh, suggesting high mutual solubility. So nickel and copper are totally soluble in one another for all proportions from 0% to 100%. Any questions? I hope you can use your own language to tell people that why this nickel copper they called isomorphous the phase diagram. The phase diagram. First, the determination of phase presents. Okay, so this if we know the temperature and the composition, then we know on which phase or phases are present. Still use this example. For example, at the point A, 1100 degrees C, 60 weight percent of nickel. And here you can see very clearly we have a solid alpha solution, solid alpha phase. On B point we draw this is the temperature, so this is the corresponding and composition. So will you know that B point is located between these two curves, between the solids and the liquids. And as a result, we know at this point, and we will have two different phases. One is liquid, one is solid. And rule two, and we can, if we know the temperature and the composition, then we can determine the composition of each phase. The composition of each phase. For example, C0 equals 35 weight percent, 35 weight percent from D to A. Okay, so vertical line, and for the vertical line, all the points on the same vertical line and have the same composition. So at TA, which equals 120 degrees C, and we know that only liquid uh, phase present, and which means that the Cl equals C0 and equals 35%. And also at temperature D and 1190 degree, and we also know that here there's only one phase present, and phase alpha, and we know that C alpha composition of alpha equals composition, this composition equals 35% nickel. Questions so far? And then we look at this temperature B. Temperature B is special because at this point we have two different phases. One is L, one is alpha. And we know that on Cl, okay, if we draw a line here, draw a horizontal line, this horizontal line intersects. So this liquid is at this point, and we can get this guy is 32% for liquid. If we draw a line, horizontal line intersects at this solidus curve, and this point is 43%. That means alpha's composition is 43%, and this is L here. The composition is 32%. Any questions so far? This is rule 2. And rule 3, if we know the temperature and this combination, then we can determine the weight fraction of each phase. Weight fraction. That is uh, combination. For example, C0. And C0 He by Ta, okay? Only liquid present, so weight percentage of this phase L equals 100%. At Td, only solid alpha present, WL equals 0, and W alpha equals 100%. And then we come back to a special point at point B. Both alpha and L present, but how can we calculate the weight percentage of L and alpha? And we use a lever rule. Okay, so you with a lever rule, and we draw a horizontal line. So this horizontal line intersects this liquidus curve at this point, and intersects this solidus curve at this point. And so suppose this point B, okay? So this point B and this point, and they form an arm. So this point B and this point, they form the second arm. We have two arms, arm 1, arm 2. And then how can we calculate the percentage? WL, okay, so these two guys, they have the same denominator, but the numerator is different. And be very, very careful. WL, the numerator for WL equals the arm of to the right of this point B. And on the contrary, the numerator for W alpha is the length of the arm and to the left of this point B. So this is called a lever. This is a lever, right? The lever denominator is the same, numerator is different, and the numerator is different. Be very, very careful. So they call the lever rule. Okay, so this is the lever rule. Um, so this is a tie line. Okay, this is a tie line. This line is called tie line, and this is a lever rule. Connects the phase in equilibrium with each other, also sometimes called isotherm. Isotherm is the same temperature. And what fraction of each phase? Think of the tie line as a lever, and theta tot, theta totter. You can see here R and S. Right? So this R and S. If these two guys are in the balance, and we know the relationship between ML and M alpha. Right? So this is WL, right? WL equals S here divided by R plus S. W alpha equals R this side divided by R plus S. Any questions so far? That means the shorter arm, okay? The shorter arm. If this phase has a shorter arm, so this guy, the weight percentage is higher. If this guy, this length arm has a higher value, then this guy's the corresponding weight percent is lower, and just like this one. The shorter arm, the point, the mass of the shorter arm this is a shorter arm here. This is shorter. So this is ML. Let me see. Let me put it this way. Okay, so So this ML, eh, you can see MA multiplied by S. So this is force multiplied by arm equals ML multiplied by R. And so you need to be very, very careful. The product of these two guys equals the product of these two guys. Then if the mass, the higher mass, and we will have the the higher arm will have a lower s, a lower mass. The same thing for this case for our phase diagram. Other questions so far? No question? We move on to the next step. And then we talk about the cooling of copper nickel alloy. So this is the very, very important one. On phase diagram, copper nickel system. And so here, and we did not from this is denote from 20 to 100, from 0 to 100, and we only focus on this point because this point is 35. And consider microstructure changes. Let's see how the microstructure changes that accompanies the cooling of C0 35% weight, 35% weight. Um, Schematic representation of the development of microstructure during the equilibrium solidification. And from solidification means the material becomes the solid from the liquid, right? And the phase equilibrium is continuously maintained. And we just assume the phase equilibrium is continuously maintained. Let's see what will happen here. This point, we lower the temperature. Let's see what kind of the microstructure we can have. At point B, at point A, let me see. At point A, and we have the uniform solution liquid, which has 35% weight, 35 weight percent of nickel. And when this is the temperature goes from A to B, go lowering down, its temperature is lowered down, and at this point B, so this curve, this is a vertical line, intersects this uh, liquidus curve at point B here. At point B, at this point, and some, and this is some dots will start, will appear, some dots here. So this is alpha, okay, so alpha, this green alpha, 35% nickel. But at this point, okay, if we go a little bit further down, we know that, so we have liquid and we have this solid. And liquid we can get at about 35. This alpha is start at this point. Alpha's with percent of nickel is 46. Do you understand, guys? So at this point, we have two phases, liquid phase and small dots. The small dots stand for the alpha phase. Any questions so far? No question, and we just move on. And in point C here, okay, in point C, as the temperature continuously becomes lower, at this point C, if we draw a tight line here, we have 32 for liquid and 43 for liquid, and also these uh, the dots grow bigger. So this dot is alpha, and so this green is 32. This is 32 with percent of nickel. This is L is liquid. So just at this point, as this point, 24 and at this point, 24 and 36, and you can see this is the alpha, the particles in the liquid phase are growing bigger, and we know this for the liquid, it is 21 with percent alpha. For is this is the dot, this is darker, the dots, they are 36 with percent. So at point E here, okay, at point E, and we only have one single phase. Liquid phase disappeared, and we only have this alpha phase. So this alpha phase here, okay, so this alpha phase, you can see this is and different grains here. And this is grain boundaries. Any questions so far? No question. We talk about non-equilibrium this cooling. So the diffusion rates in the liquid phase are sufficiently rapid and such that equilibrium is maintained in the liquid. And here, so this is the carbonation. You can see a schematic representing this during this uh, non-equilibrium solidification of 35%. And you can see at the very beginning, right, liquid, at this point, these are darts alpha phase and liquid phase. And going down, we have this. And going down further, we have this. You can see, okay? So here and here, and so these are two circles. This is the dark circle has a higher the density, a higher the composition of nickel. And you can see you have a circle here. This is more um, of a viewers. At this point, you can see this is a non-uniform. You can see clearly the difference between this slide and the previous slide I just talked about. Why they are different? The previous one is equilibrium cooling, but here this one is non-equilibrium cooling. The temperature is very, very high. Um, the liquid phase, the diffusion rate is sufficiently rapid and such that equilibrium is maintained in the liquid. Did that make sense, guys? And the next time I'm going to ask you uh, how this slide is different from the previous slide. So chord versus equilibrium structure. And C alpha these changes as we solidify. Okay, we know that C alpha changes as we solidify. We just draw a vertical line. And for copper nickel case, first alpha to solidify has 46 with percentage of nickel. And last alpha to solidify has 35% of nickel. And so this is a slow rate of cooling equilibrium structure, and we have uniform C alpha. On faster rate of cooling, and this corn structure, okay? And see, first alpha solidify 46 with percent, and then going down, then going down. You can see, and so this is the last alpha solidify less than 35 with percent of nickel. So this is the slide actually summarize and what the previous two slides I just talked about. As I said, in our next class, I'm going to cold call some people, some students, to come to the whiteboard and to explain and why these two slides are different and to the whole class. All right, and as I said, I'm going to cold call. And now don't have any idea who I'm going to ask to answer these questions. But I would at that moment I'm going to pat my head and think about the student's name and then just call. Okay, and I hope you fully um, enjoy today's class. I think it is very, very important. Make sure you understand all these concepts very, very much. So as I said, phase diagrams is the most important topics. Is a most important topic in the material science class, and it is shows the beauty of the the physics in this is the solidification of material. And so this is we will spend a lot of time on this is phase diagram, especially for this the iron carbon the phase diagram. Any questions so far? If there are no questions, I'm going to end today's session and I will see you next class. Thank you. Bye bye.